Okay, today we're going to talk more about area enclosed between two graphs or a graph in the x-axis or the y-axis and using integrals to help us get our solution. So the first problem, let's find the area enclosed by the graph of this function f of x and the x-axis. Step one would be to take a look at the graph. So there's a picture of it. So now the area that we're talking about is going to be this area here and this little tiny piece in there. Now this problem says nothing about integrals, but I'm going to use integrals to solve it. So what I have to remember is that an integral gives you signed area. This question is just asking about area in general. So all the area that it wants is considered positive. When I use an integral for the red section, I have to realize that that'll give me a negative amount. So I'm going to have to actually subtract that integral, that part, to get my total area combined. So we need to figure out, first of all, where the graph crosses the x-axis. So we can set our function equal to 0. And then choose what's the best technique to solve and find all the possible zeros. Now, just looking at the graph by inspection, it seems like our zeros are at x equals -1, +2, and +3. And you can verify that that indeed is the case. So those are my zeros. So to represent the green area, I'm going to do the integral from -1 to 2 of my function with respect to x. And then I'm going to subtract the integral from 2 to 3 because that's going to give me a negative amount. So therefore I'll be adding that for the same function. Now let's use a calculator to speed up the process. And I won't even bother going to the screen. I'm just going to punch in my function right here. X cubed minus 4x squared plus x plus 6, comma, my variable with respect to x, comma, my lower bound, -1, comma, my upper bound. So I get 11.25. All right, so now let's go ahead and do the same thing except changing it to be from 2 to 3. So I'll just recall that same command. Change my limits of integration. -0.583 repeating, which seems to be like a fraction we've seen before. -7/12. And that makes sense because it should be a very small area according to my graph. So let's take that answer. And we get 11.83 repeating, or 71/6. And thus the total area enclosed by this function in the x-axis is 11.83 repeating square units. Okay, let's go on to another problem. And this is section 22b in our textbook, area between two functions. Calculate the integral from -1 to 3 of this function. Well, doing it by hand, let's take the antiderivative. And then plug that in and evaluate and see what we would get to save time. Or maybe to not save time. Let's go ahead and evaluate this integral from -1 to 3. And as you see, we get 10.6 repeating, which is different from the answer we got with the opener. Because just using an integral on this, it's taking the first area, which I had done in green, as positive, and the second area, which I colored in red, as negative. And so it's actually subtracting those two amounts. So this question is actually quite different from the opener. Or 10 2/3. So keep in mind, if a problem is asking for area, and you're going to use integrals to help you figure that out, you have to adjust for the integrals giving you signed area. If a problem asks you to calculate an integral, then it's expecting that you're going to be doing signed area. Let's look at another example. Find the area between this curve and the x-axis over the interval -1 to 2. At any point during these examples, you may wish to hit pause, try and work the problem out, and then verify it with my solution. Okay, so here we go. First thing we want to do is look at the picture of the graph. And there we have it. So we want the area between the curve and the x-axis from -1 to +2. So if I'm going to use integrals for this, which I am, I'm going to have to realize that the first amount in red is going to be negative when I use an integral. So I'm going to have to take the opposite of that. And the second amount will be positive. So I need to find out where the 0 is for this function. Now you can see I've already calculated the 0 using my graphing calculator. And the 0 is at x equals 1.324718 approximately. Now I don't want to round that number and write my integrals out. So what I would like to do first is write it by hand, and then I'll show you how to do it on the calculator. So we want to do the integral from -1 to this x value, this 1.324 value. I'm just going to call that a. And what I can do is at this point on my calculator, I can quit out of there, and x currently has that number stored in it. So then from the home screen, I'm going to hit x and the store button and then alpha A and enter. And that'll store this permanently in A until I go back and change it for another problem. And then I can go back to the graph and doing anything on the graph will be changing my x values, but I don't have to worry. A still has that 1.32 number in it. Now, I'm going to have to do the opposite of what that gives me because it's going to give me a negative amount. So I'm going from -1 to that a value of my function. And then I'm going to add to that the integral from a to 2, which will give me a positive amount, and that should give me my answer. So this is how I would type it in one line on the calculator. I'd go to Math 9. If you still have the fnint function on there, it's a little more tedious, but with the newer operating system, you get the better graphics. But that's exactly what I had written down. Now in y1, obviously, I stored my function. So the area winds up being 3.6145. Well, let's do another example. Find the area between the curves y equal cosine x and y equals sine x from the interval pi over 4 to 5 pi over 4. First of all, we're dealing with trig functions, so we want to make sure that our calculator is in radian mode. And then we want to go ahead and look at the graph. If you want, you can pause and work this out on your own and then check the answer. So here's our graph. And we're looking for this area. So fortunately, over the interval that was specified, the sine function is always above the cosine function. So an integral is going to be pretty straightforward. Upper function minus lower function. And that should do it. So we can calculate this by hand, or we can use our calculator. Let's do this one by hand if we can do it quickly. Antiderivatives. All right, cosine of 5 pi over 4 is negative root 2 over 2, but there's a negative, so it's positive root 2 over 2. Same thing for sine. When I plug in pi over 4, so I wind up getting square root of 2 plus square root of 2, which would give me 2 root 2 for an exact answer. Let's check on the calculator. fnint with respect to x from pi over 4, 5 pi over 4, I'm sorry. Which does not look correct. Oh, I actually punched in the antiderivative. Even teachers make mistakes. We're doing sine of x minus cosine x. That looks better. 2.828 approximately. Which is the same as 2 root 2. All right, another thing I wanted you to think about, though, is another visual interpretation of this problem would be to consider one single function, which was sine x minus cosine x, and then finding the area between that and the x-axis. From pi over 4 to 5 pi over 4. And we wind up getting the same answer. All right, let's try another example. Find the area of the region enclosed by y equal 1 minus x and y squared equals x plus 1. Now this second graph is not a function. So we're going to have to think of this a little differently or make it very difficult to work out. Here's my two functions. Y equal 1 minus x is the blue line, and then the y squared equal x plus 1 is the red sideways parabola. We want to find the area between those. So we're trying to find all this area in here. Now, a more difficult way to do that would be to try and think of it traditionally in terms of doing an integral with respect to x, and then we could maybe go from -1 to 0 and get that, and then double that answer to get all of that. And then we could split up the other parts if we wanted, maybe get in this triangle, and then we're going to have to figure out this part, and then the difference between those functions, and that's going to take quite a bit of work. Alternatively, if we think of it as one chunk like that, and look at our graph sideways, so much for that. And we integrate this with respect to y, we should be able to do it in one shot. So let's rotate this back and this. And so what we need to do is find these 2 points. I'm sorry, not that one. That one. And then we want to integrate from that y value to that y value. So let's see what this is going to look like. We want to do the integral. Now we have to verify the intersection of these two functions. We can do that by maybe a substitution. And we should find that they intersect at y equal 1 and y equal -2. And those are going to be our limits of integration. Now, we're going to have to write our functions in terms of y. So the first one we can write as x equals 1 minus y. That's the blue function. And as we look at this sideways, the blue function would be on top or above the red. Minus the lower function, which will be the red. So we have to solve that for x. And unfortunately, when we try and do that, or not unfortunately, because we're looking at it sideways, we're going to get x equals y squared minus 1. But we're doing things in terms of y. So we should be able to take care of that, anti-differentiate, and get our solution. So we plug in 1, and then negative 2. So we're going to get negative 9/3, which is negative 3 minus a half plus 8. So we're going to get 4.5. And we can double check that with the calculator. We're doing the integral of, actually, if you've never done this with respect to y, I can punch it in that way too. Negative y squared minus y plus 2 comma, with respect to y, from negative 2 to positive 1. And we get the same answer. Okay, last problem. Find the area bounded by the region with the curves y equal x cubed plus 2x squared and y equal 0.5x squared plus x. Here's our picture. So we're going to need that area, and then this tiny little area inside there, which means we're going to need our intersection points of our graphs. So there, there, and there. I'll call this A, B, and C. So to find A, B, and C, we need to set these two equations equal and solve. Maybe by inspection we can check. It looks like negative 2 would work. So negative 2 does work. It also looks like 0 works. And yes, y equals 0 when x equals 0 for both those equations. And then we have this other point which we're going to have to figure out by either algebraic methods or using our calculator and calculating the intersection point, like we did with that other decimal a few problems ago. So I guess I'll replace the a with negative 2, the b with 0. And so we're going to have to do the integral from negative 2 to 0 of the blue function minus the red. Blue was the cubic, so and then plus the integral from 0 to whatever the value of c is. Looks like maybe a half of the red function, which is on top this time, minus the blue. And I'll leave the calculations to you. So hopefully that helps finding the area between certain curves. And once again, don't forget to always think about integrating with respect to y, because it might simplify your problem. The assignment for today are problems out of section 22A, which is a continuation from the other day, and then some problems from 22B.